Look at this answer. It lost 2 marks instantly, and the student didn't even know why. If you're preparing for your IGCSE Physics 0625 exams and your strategy is just time one swing, you are falling for the ultimate measurement and timing chess trap. Today, we're decoding the exact Cambridge source material so you can secure those top band grades and stop bleeding marks on simple practicals.
So why exactly did this pendulum answer lose 2 marks? The student was asked how to measure the period of a pendulum, and they literally wrote, time one swing with a stopwatch. I mean, it sounds totally logical, right? But if that's your exam strategy, you've already lost the game. You've walked right into a massive trap, because this completely ignores the inherent uncertainty of human reaction time and the precision of your instruments.
This brilliantly illustrates the difference between an ordinary guess and a top-band answer that actually locks in the method marks. The flawed approach is just way too brief. It lacks scientific rigor. The top-band answer, though, it gives a highly precise method. You don't just measure one swing. You measure several oscillations, tracing the full path from A to O to B to O and all the way back to A. And then you mathematically find the average. That is exactly what the examiner wants to see.
We're going to use this specific 4-step framework to literally outsmart the examiner. It decodes the source material's hidden rules on time, precision, and data measurement. Every single time you tackle a practical or data analysis question, you need to step through this. What's the concept? What evidence or data are you collecting? What is the scientific reasoning for your method? And finally, are you using the precise examiner wording to describe it? Lock this progression in your mind right now.
To truly grasp precision, we have to look at how time is actually built. The unit of time relies on constantly repeating oscillations, all the way down to atomic energy changes. Historically, a second was based on the length of a day, but the Earth's rotation just isn't perfectly consistent. So modern physics demands ultimate precision. According to your text, the second is now strictly defined as the time interval for a certain number of energy changes to occur in a cesium atom. It's all about hyper-reliable, repeating patterns.
Section 1. Timing weapons. Choose the right timer. To win these marks, you must choose a timer perfectly matched to the specific task at hand.
You can't just casually write, use a timer for every physics experiment. The source material is ruthless about matching the instrument's precision to the duration of the event. A stopwatch is totally fine for a pendulum, but you absolutely need a digital clock or a data logger for millisecond events, like the speed of sound. Traditional clocks use an oscillating balance wheel. Digital ones use a quartz crystal. But notice the application here. Standard stopwatch for seconds. Photogate or ticker tape for quick motion. Writing stopwatch for a millisecond event will absolutely cost you the mark.
So, how do we actually improve accuracy when measuring these tricky intervals? What's really interesting here is that the source text explicitly gives us the examiner's secret for accuracy. Whether you're timing a swinging pendulum or a ticker tape pulling through a machine, human reaction time introduces a massive percentage of error if that interval is too short. So we need a fix.
And the fix is measuring multiple events. You must state that you measure several oscillations or ticks to find the average value. Avoid the trap of single event timing completely. Instead of measuring one tick on a ticker tape, use 10. Instead of one pendulum swing, time 10 or 20. By measuring a longer total time interval, your clumsy human reaction time becomes a tiny, insignificant fraction of the overall measurement that drastically improves your accuracy.
Section 2, the pendulum practical. This is a classic 0625 setup, so let's break it down. Let's apply our strategy directly to this syllabus staple using a string and a metal bob. The examiners love testing if you actually understand the physical mechanics here rather than just memorizing a formula. Remember, one complete oscillation is not just going across. It is the full journey from A, through the center O, to B, and all the way back to A. The text explicitly tells us to release the bob so it oscillates through a small angle, but the trap is the path itself. If you only measure from A to B, you've only measured half an oscillation. Track it all the way back. These definitions are absolutely non-negotiable for your exam. They link the physical movement directly to your calculated variables. Period, represented by a capital T, is the time for that full A to B to A journey. Frequency, lowercase f, is how many of those complete journeys happen every single second, and they are inversely mathematically linked. Frequency equals 1 divided by the period.
Now, I want you to pay close attention because if you miss this next calculation rule, your perfect data collection will still drop a grade boundary. In a moment, I'll show you the examiner clue regarding significant figures that changes the frequency answer completely. But first, you need the framework that makes that clue obvious. Let's look at how we process the raw data. Check out our evidence table.
Notice we didn't just do this once. We did 3 separate trials of 10 oscillations each, getting 14.5 seconds, 14.2 seconds, and 14.8 seconds. This is what real, high-mark practical data looks like. It acknowledges that absolutely no single reading is perfect.
This equation right here is your scientific reasoning step to confidently determine the period of your pendulum. First, you average those total times together. Then, you divide that final average time by the total number of oscillations, which was 10. That gives you a highly accurate period for just one single swing, completely bypassing human error.
Section 3, the sig figs trap. Please, whatever you do, don't lose easy marks here.
Let's dive right into the trap where most students instantly lose their hard-earned calculation marks. You've collected your data, used the right formula, punched it into your calculator, and boom! It spits out a long string of decimals. What do you actually write on the answer line? Look at this length measurement from the source material, 7.180 centimeters. Looks incredibly specific, doesn't it?
Pause and predict your answer right now. How many significant figures are there? If you said 3, you just fell right into the examiner's trap. It's so common to look at a number like this, see the 7, the 1, and the 8, and completely dismiss that trailing 0 as meaningless. But in physics, that 0 is speaking directly to you.
That number has exactly 4 significant figures. The 0 at the end counts because it indicates the precision of the measuring instrument used. By writing that 0, the examiner is telling you, I measured this exactly to the thousandth of a centimeter. It isn't 7.181, it isn't 7.179, it is exactly 7.180. That 0 is a measured, highly significant digit.
And this brilliantly illustrates why you cannot just write down every digit your calculator gives you. You have to match the significant figures of your data. Look at the source text example of a rectangular block. The inputs are 4.1, 2.8, and 2.1. These all have 2 significant figures. The calculator says the volume is 24.108. The flawed answer writes all 5 of those digits. The top band answer, it knows your final result can only be as precise as your least precise input. You must provide the final volume to an appropriate number of significant figures, rounding it nicely to 24.
Section 4. The perfect exam answer. Time to apply the framework.
Let's bring all of this together to make your final exam answer bulletproof. We've navigated the timing traps, the oscillation path, the accuracy methods, and the sig fig rules. Now, lock in this exact framework, because this is speaking the specific language the Cambridge mark scheme demands. Concept, time multiple oscillations. Evidence, A to O to B to O to A, repeated 10 times. Reasoning, divide total time by 10. And examiner wording, you clinch the final mark by writing, calculate average to reduce uncertainty.
Run every single practical or data analysis answer through this mental checkpoint before you even think about turning the page. Are your units there? Missing a lowercase s for seconds or Hz for hertz will cost you. Did you round to the appropriate significant figures? Did you spot any wild anomalies in your trial table that shouldn't be averaged? And most importantly, did you average multiple readings?
You now know exactly how to dodge the timing and significant figure traps for a pendulum. But the source material pushes us to consider one more tricky variable: ticker tape data analysis. It requires a completely different approach to identifying short time intervals in motion, and it is the absolute favorite follow-up question examiners use to catch you off guard.
If measuring a simple pendulum requires atomic-level definitions of time and strict significant figure rules just to get an accurate reading on paper, imagine the precision required for ticker tape data analysis. If you don't know this linked skill, you'll still lose the match. The next clue is in video B. Click the video on the left side of your screen right now to master this crucial follow-up skill. And make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button on the right, and I'll see you in video B for your next checkmate.